In the movie Ice Age, this hapless character is frozen in a solid block of ice and then effortlessly thaws out 1,000 years later. In the real world of cryobiology, things aren't that simple. When tissue is slowly cooled, ice crystals first form between cells, and then eventually, as cooling continues, the cells become squashed into pockets of concentrated salt solution. Now, this brings us to the first myth of cryobiology, which is the common belief that freezing bursts cells. In fact, the complete opposite is true, that under conditions of slow cooling, freezing squashes cells. It doesn't burst them. More than 50 years ago, it was first discovered how to use cryoprotectants to reduce the damage that occurs during freezing cells. Some of the common cryoprotectants are glycerol, DMSO, and ethylene glycol. When tissue without cryoprotectant is cooled, the salt water inside tissue converts almost completely to ice. But if you first add just a dash of cryoprotectant before you cool your cells, the freezing process concentrates the antifreeze cryoprotectant in the unfrozen water outside the ice crystals, lowers the melting point, and limits the extent of ice formation that occurs so that there's a larger volume of unfrozen solution in which cells can continue to survive. So instead of having a situation like this at very cold temperatures, if cryoprotectants are present, you have a situation like this where there's more room for the cells to survive. There's a large number of different types of cells and even tissues that can be successfully cryopreserved by freezing. Still a problem with freezing if you want to adapt freezing to large organs, and that's that although individual cells can survive in between these ice crystals, the ice crystals break up the delicate connections between cells, and for most organs that prevents recovery of function of the whole organ. A solution to this problem was proposed by my colleague Greg Fay more than 20 years ago when he proposed vitrification as an approach to cryopreservation. The idea with vitrification is you begin by loading tissue with so much cryoprotectant that freezing can't occur at any temperature. So during the whole process, you just have a liquid solution, and as you continue cooling, the liquid becomes thicker and thicker like syrup, then like molasses in January, and then finally, as you go below about minus 100 degrees Celsius, the solution converts to what's called a glass, which is a solid substance where everything is stopped, but there's no ice crystals in it, and that's the state of vitrification. On a level of a tissue, it looks something like this. You start with your cells, nice and happy, and then you add your cryoprotectant, then you begin cooling, and then even when you reach very cold temperatures, the state of the tissue is unchanged because there's no ice crystal damage, so there's no structural damage to the tissue, and it can remain in this stage practically indefinitely. This is what happens during freezing if you have a dilute solution of cryoprotectants. If you don't have enough cryoprotectants mixed with water to vitrify and you cool, your water just becomes filled with millions of tiny ice crystals. But if you have enough cryoprotectants in the solution to vitrify, you can cool to extremely low temperatures and everything still looks like a liquid. Although in fact, it's not a liquid, it's a solid, because the temperature that's being read here is actually minus 124 degrees Celsius. And at that temperature, what was formerly a liquid is now a solid, even though it has no crystals in it. And now this famous photograph shows what vitrification looks like on the scale of organs. On the left you have a frozen rabbit kidney, and on the right you have a rabbit kidney that's been protected by a vitrification solution and then cooled to minus 140 degrees Celsius. There's no visible signs of damage. Time is essentially stopped for that organ. And what's now been shown possible just a few years ago is you can rewarm an organ the size of a rabbit kidney, unload the cryoprotectant, and implant that kidney back into a rabbit and have it support the animal's life long term. This brings us to cryobiology myth number 2, which is sometimes stated in media, is that cryoprotectant can't penetrate into organs. In fact, it can, because you can circulate cryoprotectant through organs just as blood circulates through organs. Essentially, you can replace the blood with cryoprotectant and thereby introduce cryoprotectant to all the cells in the organ. This process is called perfusion. This is an organ perfusion machine that's used at 21st century medicine to prepare organs for vitrification. There's an organ chamber and there's a rabbit kidney inside there right now, a tube called a cannula attached to the renal artery that is pumping cryoprotectant into the organ, preparing it for vitrification. Just as for freezing, there's also a very large list of tissues that can now be successfully cryopreserved by vitrification, the most sophisticated of which is the rabbit kidney at this point, but we hope to eventually get to larger success with larger organs as well. As you attempt to scale up vitrification to large organs, there's a few problems you run into. The two most serious are a slow heat transfer in large systems, and that limits the rate that you can cool large organs, and the time it takes to cool large organs allows time for the toxicity of the concentrated cryoprotectants to accumulate and under some circumstances poison the organ. So with vitrification, you're always walking a tightrope between avoiding ice formation and avoiding toxic effects of the vitrification solution, and that's the tightrope that we're attempting to lengthen in the field of vitrification research and medicine. All right, that brings us to cryonics. Cryonics can be defined as the cryopreservation of a person with medical needs that cannot be met by available medicine until resuscitation and healing by future medicine is possible. Note that cryonics, correctly defined, is not the cryopreservation of dead people, because obviously if the process were to ever succeed, then that person was never really dead. So that's not a correct way to really look at it. Cryonics includes cryopreservation by methods not currently reversible. It includes dealing with medical problems that are not currently addressable. And it includes cryopreserving people with problems so severe that they may not even be recognized as problems by contemporary medicine. An example of that would be the kinds of injuries that happen to a person when their heart stops for a prolonged period of time, such as a couple of hours. What do cryobiologists say about cryonics? Well, probably the most famous expert opinion about cryonics is a quote that's been circulating in the media for more than 20 years now, and it's credited to my colleague Arthur Rowe, who has stated that believing cryonics could reanimate somebody who has been frozen is like believing you can turn hamburger back into a cow. Well, I'll do you one better than that. Not only can hamburger be turned back into a cow, I will tell you how you can turn hamburger back into a person. You eat it. I mean, the take-home message here is that with sufficient molecular manipulation, hamburger can be turned back into healthy tissue, either a cow or a person. And this tells us that whether one form of matter can be manipulated into another form of matter is really the wrong cryobiological question. What do other cryobiologists say about cryonics? Well, here's a quote that you'll never see in the media because it's too boring. Cryobiological issues of cryonics are complicated. The most complicating factor is that cryopreservation is time travel. This fact is not in dispute. If you ask any cryobiologist, they will tell you that if you cool tissue to a sufficiently low temperature, it can be preserved essentially indefinitely in an unchanging state for centuries or possibly even thousands of years. The problem is that this fact is seen as largely academic in the cryobiology community, because in medical cryobiology, as it now exists, there's no need to cryopreserve things for centuries, and people just don't spend a lot of time thinking about the technological implications of keeping things stored for centuries. But the fact that you propose to store for centuries does mean that the feasibility of cryonics must be evaluated based on technologies that don't yet exist, but that can exist according to physical law. To think about these things, I think it's helpful to consider a plot of injury reversibility versus injury severity. I think we can all understand intuitively that as the severity of an injury increases, it becomes less and less likely to be a reversible injury and more likely to be an irreversible injury. And there's also a time dependence to this plot. In the year 2000, we can now reverse injuries that are more severe than medicine could reverse in the year 1900. The classic example that's used of this is cardiac arrest. If someone's heart stops, there wasn't much that could be done in the year 1900, but that particular injury can be reversed often in the year 2000. Unfortunately, with human cryopreservation or cryonics, you're dealing with an injury during the cryopreservation process that is so severe, it's way off the scale of injuries that are currently reversible. And the general conception of the problem is that the problem is so severe and the status quo in medicine is so eternal that this situation will never change, that for all intents and purposes, cryopreserving whole humans is useless because the injuries are essentially permanently irreversible. But what people who've looked at this problem hard and seriously have found, and that would be such as some of the people who've been speaking at the conference here this weekend have found, is that that's not quite the case. That if we look to the limits of what medicine is going to be able to do decades or even centuries in the future, there's going to be large classes of injuries that are presently irreversible that will be reversible in the future. That means we really have to consider a third class of injury, which is future reversible injury. All right, what are some of the technologies that we have to take a serious look at if we're going to consider the medicine that's going to be available decades or centuries from now? Well, one of the most important parts of foreseeable medicine is going to be advanced tissue regeneration technology. Within this century, we will see technologies developed for teaching the body to regrow lost limbs, for example. And at the farther frontiers of medicine, it's possible to foresee technologies where patients who've suffered severe trauma can be placed on artificial life support until vital organs can be regenerated. In fact, according to the laws of physics and principles of biology, there is no reason why it would not be possible to program cells on the surface of just even a brain, or even just one cell on the surface of a brain, to initiate a growth process that would eventually regrow a whole body around just a brain, if that's all that was able to be recovered from a victim of trauma. Now, in case this seems fantastic, let me remind everyone that generation of whole bodies starting from a single cell is a technology already demonstrated in nature. This is not molecular nanotechnology. This is not anything exotic. The generation of the production of tissue and organs is a normal business of biology that living things have been doing for hundreds of millions of years. It is just a matter of us learning to steer these processes in a direction of therapy and not just reproduction. An area where nanomedicine becomes very important and in fact indispensable is for repairing the brain in cases of severe injury, because the brain is obviously the one organ that we just can't casually replace. Fortunately, or it's been very gratifying to see over the last 20 years that nanomedicine, at least in some of its forms, such as organic conceptions of it, is becoming an almost mainstream view. Even the National Institutes of Health website on nanomedicine makes reference to synthetic biological devices that could heal diseases and fix broken parts inside cells. So there is an emerging consciousness and awareness that these kinds of capabilities are coming downstream in medicine. What we have to look at in terms of the ultimate limits of nanomedicine are extremely advanced technologies for analyzing the molecular content of a brain and performing arbitrarily complex molecular repairs inside the brain. And the implied ability from such nanomedical capabilities is the ability to extract all molecular information content of arbitrarily injured tissue and reconstruct an inferred healthy state. Now, remember, we already said that with sufficient molecular manipulation, we can turn hamburger back into healthy tissue. That's proven in nature. The extension of that is that with sufficient molecular manipulation, any injured tissue can be turned back into healthy tissue. But the question is, how much information can be missing about the original state of tissue before a repaired person is no longer the original person? And that brings us to the information theoretic criterion for death, which was discussed yesterday. A person is dead according to the information theoretic criterion if their memories, personality, hopes, dreams, etc. have been destroyed in the information theoretic sense. That is, if the structures in the brain that encode memory and personality have been so disrupted that it is no longer possible in principle to restore them to an appropriate functional state, then the person is dead. If the structures that encode memory and personality are sufficiently intact that inference of the memory and personality are feasible in principle, and therefore restoration to appropriate functional state is likewise feasible, then in principle the person is not dead. So clearly the brain is the key to reversibility of injury in future medicine. And this brings us to the key cryobiological question of cryonics. Does cryopreservation preserve sufficient brain information to permit recovery of the original person? At this point, I have to digress onto a side issue because it's such a common misconception, and that's the question, does stopping a brain kill it? This is a quote from a standard textbook of medical physiology. We know that secondary memory does not depend on continued activity of the nervous system because the brain can be totally inactivated by cooling, by general anesthesia, by hypoxia, by ischemia, or by any method, and yet secondary memories that have been previously stored are still retained when the brain becomes active once again. Therefore, secondary memory must result from some actual alterations of the synapses, either physical or chemical. This means that our brains are not like random access memory in a computer, volatile memory that's lost when power is turned off. Our brains are more like a computer's hard drive in terms of the way they store long-term memories. There are clinical examples of brain inactivation that many people have survived. If your heart stops more than 30 seconds, all your brain electrical activity will go silent. Barbiturate coma can turn off brain electrical activity for days at a time. And hypothermia less than 18 degrees Celsius will also generally silence all brain activity. The first study attempting to cryopreserve brains was conducted by Isamu Suda back in the 1960s. He froze cat brains with 15% glycerol and then reperfused them with warm blood. He found he could actually recover normal electrical activity after 5 days frozen at minus 20 degrees Celsius. But when he attempted to measure electrical activity after 7 years of storage at minus 20 degrees Celsius, he only found partial return. This tells us that minus 20 degrees C is just too warm for long-term storage. He found, however, partial return after another period of time at minus 60 degrees C, and no return of integrated electrical activity after minus 90 degrees C, which means those temperatures were cold enough to injure the brain beyond the point of recovery of electrical activity. And we can understand why that is by looking at our concept of what happens to cells when they freeze. If you don't have enough cryoprotectant around the cells, and when you get to very low temperatures, the cells will become separated from each other and integrated organ function will no longer be possible. And I should mention that Suda did find that when he cooled brains to very low temperatures, he could still recover what he called unit electrical activity in single cells. It's just that they weren't able to talk to each other because the freezing damage was so severe. One way to deal with this problem is to increase the cryoprotectant concentration. Instead of 15% cryoprotectant, you can start with 40%, and then you get less volume converting to ice. In fact, you can increase it to even greater concentration, such as 60% glycerol, and then you get very little ice, and most of the tissue volume is going to be preserved in a vitreous, glassy state. This brings us to the largest study of brain cryopreservation published to date, which was effective human cryopreservation protocol on the ultrastructure of the canine brain, performed by Mike Darwin and collaborators at the cryonics company Biopreservation back in 1995. And he showed after brains were treated with 60% glycerol and cooled to deep sub-zero temperatures, and then rewarmed, that there was remarkably good structural preservation. This is an electron micrograph at 6,700 times magnification. These holes here are actually capillaries, blood vessels, so they're supposed to be there, and they have nice smooth walls, looking generally very uninjured. These round blobs here with dark black boundaries are axons, and the myelin, which is the black outline around the axons, is generally intact. There's just a few spots where it kind of turns a bit foggy. And also you have a problem of chromatin clumping in cell nuclei, which is very commonly seen in cryopreservation. This is a closer up view, and here we're actually looking at synapses, which are the points where nerve cells communicate with each other. And you can actually see that they're very well preserved. And this is an extreme close-up of a synapse. And what's really gratifying to see here is that not only can you see junction between the cells, but you can actually see these tiny circles in here, which are neurotransmitter vesicles, which is a very fine, structured, and important part of that aspect of brain anatomy. And it's very suggestive that the essential biochemical nature of the synapse is being preserved. Here we have a close-up of some axons again and the myelin around them, and you can see that there is some damage to the myelin where it becomes indistinct here. There's a close-up, more damage to the myelin. And this is a view of just the brain's white matter, which consists entirely of axons. And you can see a cross-sectional view here through lots and lots of fibers and lots and lots of myelin sheaths. And it all generally looks pretty intact. In some parts of these brains, there is ice damage. There's holes apparently produced by ice crystals. And this is not unexpected because at that concentration of glycerol, we know ice has got to form somewhere. And if you look every 20 or 30 microns or so, there is a hole there. So there is still freezing damage occurring. So what we like to do is eliminate that freezing damage completely. The technology I showed you of perfusing with approximately 60% glycerol was the technology used in cryonics during the 1990s. And into the 21st century, we moved to true vitrification solutions, which is solutions that are approximately the same concentration as the old 60% glycerol, but a different composition that is more resistant to ice formation and that allows the entire tissue volume to be cooled without ice formation. And this brings us to cryobiology myth number 3, which is the belief that only tiny things can be vitrified. In fact, any size tissue can be vitrified, even at slow cooling rates, if you use a sufficiently high concentration of cryoprotectant. We've already seen this photographic illustration of that, where here you have 5 pounds of vitrification solution that's completely ice-free. And this is, in fact, the vitrification solution M22, which is used both to cryopreserve kidneys experimentally and used in Alcor's vitrification procedure. There's a catch, though, and that catch is you can vitrify things as large as you want, but vitrification of large organs with current technology will often result in loss of viability. Viability being defined as the ability to spontaneously recover due to biochemical injuries caused by the cryoprotectant solution. But as far as structural preservation goes, that was studied in a publication in the Annals of the New York Academy of Sciences 2 years ago. The title was The Arrest of Biological Time as a Bridge to Engineered Negligible Senescence. It documented the use of M22 to cryopreserve rabbit brains and found on extensive micrographs, transmission electron micrographs taken through vitrified, rewarmed rabbit brains, that there is no evidence of ice formation anywhere in the brain. This is an electron micrographic shot of the hippocampus of the brain, and there's extremely dense preservation of the gray matter of the brain, and there's just no sign of ice crystal damage anywhere. If you zoom in, you do see signs of other damage. In particular, you have these white streaks here. And these are caused by dehydration, where this concentration of cryoprotectant, which doesn't penetrate the blood-brain barrier very well, it only penetrates it partially. It causes a lot of water to flow out of the tissue, causes cells to contract and retract away from each other, producing these lines of dehydration artifact between the cells. And that seems to be, at least on a structural level, reversible if cryoprotectant is removed and the brain is rehydrated. This is a scanning electron micrograph. It's part of the same study. And the purpose of the scanning electron micrographs is to, again, look for signs of ice formation. And what was seen in all the scanning electron micrographs of this brain was just holes, which are blood vessels. These are sections through capillaries, actually. There's no signs of tearing or the kind of damage that would be expected if ice crystals were present. All right, what about cryopreservation under poor conditions? Poor conditions can include long ischemic time, which means time without blood flow, and that in turn can lead to limited or no cryoprotection. If cardiac arrest lasts too long and blood clots, it becomes difficult or impossible to perfuse cryoprotectant. This is a study of, I believe, canine brain that was cryopreserved with 4 molar glycerol. a lower concentration of glycerol. This would be about 35% glycerol compared to the 60% glycerol that I showed you in the previous micrographs. And here we can see more obvious signs of damage because a larger volume of the tissue is being converted to ice. So you have a large hole here where ice formed and a general lightening of the density of the image because of a sort of generalized loss of structure in some areas. And this is another area of suboptimally perfused brain where freezing injury has caused a substantial loss of structure. Now I'm going to show you something really amazing. These are a type of image called a freeze substitution image, meaning you take tissue that is still in the frozen state and you treat it with chemicals, making it possible to get microscopic light and electron microscopic images of the tissue of what it actually looks like in the frozen state. And on the left you have a scale of millimeters, and you have some rabbit brain slices here and freeze substitution images of them. And these slices were, actually these whole brains, were perfused with 3.72 molar glycerol, which is probably around a 35% concentration of glycerol. And what you see is extensive ice damage. In fact, when I look at that slice, it looks to me like frost on a window pane when I used to live in cold Canadian winters. There's more ice there than tissue. And if you zoom in to a higher magnification, you can again see the devastating effect of the ice crystals. In fact, it's not even recognizable as tissue. And if you zoom in still further, what you see is between the ice crystals, squished and squashed, there is actual recognizable biological tissue. It's just terribly squashed between all those ice crystals. But now I'm going to show you the really amazing thing. This is what the tissue looks like in the frozen state. But if you then rewarm it and allow the ice to thaw, you get something that looks like that, where most of those terrible gaps and obvious damage from the ice apparently disappears, at least on a light microscopic level. In fact, this is a section of brain tissue that was thawed after freezing, and it didn't even have any cryoprotectant in it at all. This is straight frozen tissue, which means it had, in the frozen state, even more damage than you see in this slide right here, and yet when it's rewarmed, it goes back to that state there. And there's still damage evident even on the light microscopic level, but it's remarkable how the tissue somehow seems to remember the state it's supposed to be in when the ice goes away. Recently, Dr. Sergei Shelik at Alcor has also begun to explore the question of straight freezing or freezing without cryoprotectant because it is relevant to certain classes of cryonics cases where cryoprotectant perfusion is impossible. And he's also finding that although there's extensive damage visible on these electron micrographs, you can at least usually see what is damaged. You can still generally recognize the damaged structures. It's not a process of massive obliteration of information, which is gratifying because there's been a lot of controversy over the years about exactly how damaging freezing without cryoprotectant is. And lately the pendulum is beginning to swing back in the direction that it may not be as damaging as once thought for cases that are subjected to that kind of freezing. So obviously, this is not hamburger. Even if you freeze without cryoprotectant, there is a lot of structure that's still preserved. But still, if enough damage occurs, you're going to start pushing out onto this spectrum, and eventually you're going to reach a point where so much information is going to be obliterated that the damage is permanently irreversible by any technology. So what does that mean clinically, and what does that mean for the outcome of cryonics? We've already stipulated that with sufficient molecular manipulation, any injured tissue can be turned back into healthy tissue. So what happens when information encoding memory and personality is incomplete or non-existent? And the answer is that one would expect the patient to recover with partial or total amnesia. So that means for medicine capable of completely general biological repair, survival is not a binary question. In medicine today, we're used to thinking of the patient either making it or not making it, live or die, black or white. But for really advanced medical technology, cases are rarely going to be like that. There's going to be a lot of ambiguity about exactly whether an original patient really survives after extreme biological repairs. No talk of the cryobiology of cryonics would be complete without mentioning the fracturing problem. This is a problem that occurs not just in vitrification, but in frozen tissues as well. It's just more obvious in vitrification because it can be so easily visualized. And the problem is that as you cool tissue below the glass transition temperature to vitrify it, thermal stresses build up once the tissue or the solution becomes solid. And if you cool too cold, the solution and tissue will fracture. And generally, I think the feeling is of the people who've considered this problem that this is not a process that is destroying much information, but it does greatly complicate the problem of repair because the vascular system is disrupted. It sort of pushes you from the realm where simpler biotechnologies were needed for repairs into the realm where more hardcore molecular nanotechnology will be needed for repair while keeping the tissue still at very cold temperatures. So there is incentive to reduce or eliminate this problem in cryonics because of the extra burden it places on the requirements for future repair. All right, after showing you so many horrible-looking micrographs under non-ideal conditions like this, I just want to remind you that under ideal conditions, we are dealing with this, which is excellent structural preservation. So under ideal circumstances, it appears possible to cryopreserve the human brain with little or no ice crystal damage. But current brain cryopreservation methods still aren't reversible. The remaining issues of brain cryopreservation are unknown effects of cryoprotectant toxicity, unknown effects of highly concentrated solutes on the other side of the blood-brain barrier where cryoprotectants don't penetrate, structural damage caused by dehydration, limited blood-brain barrier penetration on cryoprotectants, which it doesn't seem to be an issue for preventing vitrification, but it complicates questions of toxicity. Of course, it has now been shown possible, thanks to the support of Ben Best and the Institute for Neurocryobiology, supporting the research of Drs. Pachugan and Fay. It's been shown possible to reversibly cryopreserve brain slices. And that's important because it shows that the process of cryopreserving brain tissue in a living, viable state is possible. And if we can do it in slices with more work, we should eventually be able to succeed at that for whole brains. But we have to realize that because of higher protectant concentrations, longer exposure times, and the blood-brain barrier, cryopreservation results obtained in slices are not generally applicable to whole brains. So we can't be too excited that we reversibly cryopreserved just parts of the brain. We still have a lot of work to do before we can reversibly cryopreserve the whole brain. Another extremely important question is memory preserved by cryopreservation? And I think there are powerful arguments that it is, such as this micrograph here, which shows tremendous amounts of structure that are preserved. I think it's hard to look at these kind of data and argue a mechanism by which memory would not be preserved that's consistent with known neuroscience. However, it's not proof. It's a feasibility argument, a likelihood argument, but it's really not proof. And I've seen people who are absolutely adamant that it's not satisfactory to make a hand-waving argument about memory preservation. You really should do some experiments to show it. The best proof that a cryopreservation method is reversible in theory is to reverse it in practice. And I think that's what Aubrey was saying yesterday, and that's what I'm going to say again today. That's an extremely important message. Short of reversible suspended animation, I think the best proof that cryonics can work will be the demonstrably reversible cryopreservation of the brain in a suitable animal model. Until that's done, we, to be perfectly honest with our critics, cannot say for certainty whether cryonics today is in this zone or out here. We cannot state for certainty that we are adequately preserving memory and personality using current cryonics methods until we do the research to absolutely prove it, in my belief. So therefore, I propose what I consider to be a logical development sequence for cryobiological study of cryonics, and it constitutes a continued improvement of structural and biochemical preservation of the brain, explicit demonstration of memory preservation, reversible cryopreservation of the whole brain, continued improvement of structural and biochemical preservation of the rest of the body, and eventually whole body reversible suspended animation as sort of the ultimate goal of both cryobiology and cryonics. There's great benefits to be had from this process of continuing to improve cryopreservation methods and push them closer and closer to contemporary reversibility. The greatest benefit is that it makes cryonics what you could call a last-in, first-out process. For instance, a cryopreservation method in 2006 may leave a patient out in this zone of injury, whereas if we continue developing the technology, the cryopreservation methods of 2030 could result in much less injury, which means the difference between getting revived in the year 2100 versus getting revived in the year 2200 if you're cryopreserved with more crude methods. There's one final thought I'd like to leave you all with, and that is, because of an idea like cryonics, the distinction between reversible and future reversible injury is really rather arbitrary. If you have the means of stabilizing the condition of a patient indefinitely, the proper way to think about injury reversibility is just on one scale. It's either ultimately reversible or it isn't. And that's the ultimate limit that defines life and death. And the way to think about cryonics is that it's a way of potentially keeping people on the life side of that spectrum. And in fact, I suggest that even in cases when we're not sure how well or how much, would be more proper to say, of a person we are preserving, life should still be given the benefit of the doubt. Thank you very much. We presented this result at the meeting of the Society for Cryobiology as an oral presentation and abstract in the summer of last year. We've submitted a couple of manuscripts to journals to follow up on that, and have been told by the reviewers that they want a larger number of replications, and that's what we're working on now. In the vitrification slides, practically all the damage you're seeing is due to vitrification. With freezing, there's undoubtedly a lot more happening during rewarming, because you're doing that phase change from the solid to a liquid state, and there's diffusion going on, but there's less physical processes occurring during rewarming of vitrified tissue. So I think the micrographs you've seen are accurately representative of the state of tissue in a vitrified state. The tendency seems to be that when you get up into really high concentrations of cryoprotectant, almost everything appears to be toxic, and undoubtedly part of the reason for that is that tissue doesn't like having its water taken away from it. It is not the natural state of tissue to be soaked in 60% organic solvents. Tissue likes to have water around it, and the way we've dealt with that problem so far is that my colleague Dr. Fay has discovered that if you choose cryoprotectants that are sufficiently like water in some technical respects, that they will be less toxic. So there is progress being made on the front towards finding less toxic solutions. I think it's fair to say that ordinary chemistry, in the sense of what we normally think of deterioration of tissue, is stopped when you're even near the glass transition temperature, because not only is the rate of molecular motion very slow, but you also go below the activation energy for a lot of biochemical reactions, which causes the reaction rate to just nosedive towards zero. So I think the correct way to think about the issue of stability at warmer temperatures is not just whether or not normal tissue deterioration will continue, but whether some other deterioration mechanisms may still be active. And there are mechanisms of change that are known to be of concern at that temperature. In particular, there's a process called nucleation, which is the microscale reorganization of water into ice crystals on the molecular scale that's a concern at that temperature. But generally, it seems possible to stop that process if you're, say, 20 degrees below the glass transition temperature. You can look at the monograph that Hugh Hickson wrote years ago, How Cold is Cold Enough, where he looked at the Arrhenius equation for the reaction rate of catalase, which is one of the fastest biochemical reactions known in biology. And I think you'll find at these temperature ranges, it's still pretty slow. Brain slices have been shown in a publication in Cryobiology just this year to be recoverable after a simple vitrification protocol, in the sense that they recover normal biochemical reactions. I think that record is still held by a guy named Haneda, who back in the 1980s recovered dogs after storing them at 0 degrees Celsius with no blood flow for 3 hours. 0 degrees Celsius is the limit unless you start adding cryoprotectants, because if you go lower temperatures, you start forming ice and you get into complicated cryobiological issues. So that frontier has not progressed much in the last few decades. When you do a visual inspection of a fractured sample of cryoprotectant, I can't see the displacement by my eye, so it's got to be less than a millimeter, in fact, maybe even less than 100 microns.